Sometimes data doesn't come as averages or scores. Instead, it comes as categories: yes or no, male or female, clicked or not clicked, purchased or not purchased, passed or failed. There are no means to compare, no averages to subtract. But the question is still same. Is what we are seeing real, or could it just be random chance? For example, do men and women prefer different products? Is customer churn related to subscription type? Is exam result related to teaching method? Is disease occurrence related to lifestyle? When data is categorical and we want to test relationships, t-test and ANOVA no longer work. That's where different tool comes in. Welcome back to Sheetal's Data Desk. I'm Sheetal, and in this video we are going to deeply understand chi-square test with intuition, visuals and real-world examples. In this video, we are going to cover why averages don't help here. What is chi-square test? Core idea of observed versus expected. What is chi-square statistic? Interpreting chi-square result. Types, assumptions and common misconceptions of chi-square test. Also, when not to use chi-square test. And we will conclude this topic with key takeaways. So, let's start with problem it is designed to solve. Why averages don't help here. Imagine this. You run marketing campaign and track whether users click the ad. You collect data like this. Male users clicked or didn't click. Female users clicked or didn't click. Now ask yourself, can we calculate average here? No. Can we use t-test? No. There are no numbers to average, only counts in categories. Yet question still matters. Are clicks related to gender or are clicks happening randomly? Now imagine another case. You survey customers. It looks like premium users churn less. But again, pause. Is this relationship real or could it happen by chance? This is exactly the kind of problem chi-square test was created to solve. So, what exactly is chi-square test? At its core, chi-square test is statistical method used to test relationships between categorical variables. In simple words, it helps answer this question. Are two categorical variables related or are they independent of each other? Chi-square test does not compare averages. It compares observed count with expected counts. It asks if there were actually no relationships, what would the data look like? And then checks how far is the real data from that expectation. Let's build intuition. Imagine a classroom of 100 students, 50 boys, 50 girls. Suppose 20 students passed an exam. If gender has no effect, we would expect 10 boys to pass and 10 girls to pass. That's the expected count under independence. But what if we observe 16 boys passed and 4 girls passed? Now question becomes, is this deviation small enough to be random or large enough to suggest real relationship? This is the heart of chi-square test. It compares observed counts, that is what we see, against expected counts, that is what we would expect if variables were independent. So, how do we measure this difference? To measure this difference, we use something called chi-square statistic. Conceptually, it measures how far observed counts are from expected counts across all categories. Logic is simple. Small differences, that means likely random, and large differences means unlikely by chance. Chi-square statistic adds up how big each deviation is relative to how large expected value was. Bigger the chi-square value, stronger the evidence against independence. Once we calculate chi-square statistic, we compare it with chi-square distribution. This gives us p-value. P-value answers this question. If there were actually no relationship between these variables, how likely is it to see deviation this large? Small p-value means relationship unlikely due to chance. And large p-value means data is consistent with random variation. Important reminder is chi-square test does not tell us how strong relationship is. It does not tell us which category causes it. It only tells us whether relationship likely exists. Chi-square test is not just one single test. In practice, there are two common types and each one answers slightly different question. Let's look at them one by one. First and most commonly used is chi-square test of independence. We use this test when we want to know whether two categorical variables are related to each other or whether they are independent. For example, does gender influence purchase decision? Is education level related to employment status? Does device type affect website conversion? Here, question is simple but powerful. Are these two variables connected or not? Chi-square test of independence helps us answer exactly that. Second type is chi-square goodness of fit test. This one is used when we have only one categorical variable and we want to compare what we observed against what we expected in theory. For example, are dice rolls fair? Do customers choose options equally? Does real world traffic match expected proportions? In this case, we are not comparing two variables. We are comparing observed category frequencies with expected proportions from known model. Like every statistical tool, chi-square test also comes with assumptions. These assumptions matter because results are only reliable when tests used correctly. First and most important assumption is independence of observations. Each observation must belong to one and only one category. In simple terms, one person's outcome should not influence another's. When observations are dependent, chi-square test is no longer appropriate. Second important assumption is that expected frequency should be sufficiently large. As a rule of thumb, expected count in each cell should be at least 5. When expected counts are too low, chi-square approximation breaks down and results become unreliable. In those cases, we don't force chi-square test. Instead, we use alternatives like Fisher's exact test, which is designed for small sample sizes. Because chi-square test is widely used, it is also widely misunderstood. So, before we move on, let's clear up few very common misconceptions. First, chi-square tells us causation. No, chi-square test only tells us whether variables are associated, not whether one causes the other. Second, large sample means strong relationship. Not necessarily. With very large samples, even tiny differences can become statistically significant. Third, significant result means important result. Wrong. Statistical significance only tells us that pattern is unlikely to be due to chance. It does not tell us whether that pattern matters in real world. That interpretation, deciding what is meaningful or useful, is always human judgment. Just because tool is popular doesn't mean it should be used everywhere. So, let's talk about situations where chi-square test is not right choice. You should not use chi-square test when your data is numerical, not categorical. Instead, use t-test or ANOVA. Expected counts in categories are very small. In that case, results become unreliable. Observations are dependent. In that case, independence assumption is violated. You want to measure strength or direction of relationship. Chi-square only tests existence, not magnitude. Statistics is not about forcing one method everywhere. It is about choosing right tool for the right type of question. Now, before wrapping everything up, let's step back and bring everything together. Chi-square tests relationship between categorical variables. It compares observed versus expected counts. Chi-square statistic measures deviation from independence. P-values tell us whether relationship is likely real. Statistical significance is not practical importance. Chi-square test teaches us powerful idea. Patterns in data must be tested, not assumed. Once you understand that, statistics stops feeling like formulas and starts feeling like magic. If you found this video helpful, please like, subscribe and share it with someone learning data or analytics. This is Shital's Data Desk, where we turn uncertainty into understanding. Thanks for watching, and I'll see you in next video.